Okay, well, it just dawned on me as I turned off the video that I should have continued on, although the video was already getting kind of long there. So let me call this then heat equation part 2. Because I just got done kind of deriving this multivariable equation and talking about what the meaning behind the second derivative, the concavity of it, and the rate at which the temperature changes. And we were looking at some different examples, and we'd finished off this one about jamming a metal rod between a hot and cold spot, and how the temperature profile would evolve with time as we tried to read this equation. But what I probably also should have said is this is an excellent mathematical opportunity to look at a Fourier series or a Fourier transform, because if you had a really complex temperature profile, so here's temperature, here's X, and maybe I'll just put one end of the metal rod is maybe at 0, it gets real hot, or gets semi-hot, how's that, and levels off, but the middle has these patches of hot, cold, hot, cold, hot, cold, real cold, hot, cold, hot, cold, hot, cold, and then maybe something like that. So just a crazy profile. And going back to our first video, we would look at this and we would look at the concavities of it. And so this place where in the middle where it's cold would be a positive concavity, and it would come up. And these, what we would call these peaks here, they're hot, their concavity is negative, they would come down. And so maybe a mental profile of this would be sort of like if you had a curvy string and you pulled on it, you'd be leveling the string out. And so in this case, this would come down. These would be less wavy. This would have come up. And so maybe after a few moments in time, that would be the temperature profile before it kind of more levels off and then has a straight line, again, assuming the metal rod was connected to these reservoirs, that heat has a place to go out without the ends changing temperature. And if it didn't have any place to go out, though, the end would warm up and the whole thing would have then a solid uniform temperature on it. But I said all that in the last video. What I wanted to say on this one was then that if you do have this complex profile, so temperature versus X, and it does look like maybe it's waving in the middle and then dips cold and wavy in the middle and then goes back, you could then use a nice little property of mathematics and say that this temperature profile can always be written mathematically. It's something that looks like this. It would be a sine of some frequency, let me call it omega 1x, and it would have some amplitude, let me call it amplitude 1. And then there would be another variational frequency. It might have a different amplitude, probably does if it's in a very generalized complex function. And then we would have another one. And let me stop at 3. But as you're studying your multivariable math, and if you remember your whole Fourier series and Fourier transforms, is if we were to write this out, we might need an infinite number of terms. At some point, though, the amplitude gets really low because, again, these higher ones would be higher frequencies, and the temperature doesn't vary that much. Mine, I tried to make, some high frequencies here so that there would be some higher order terms. But here's the neat thing about it. Remember, the heat equation is really talking about the second derivative of it. And the second derivative of a trig function is really nice. So let me just take the second derivative of the temperature with respect to x. Because what you get when you take a second derivative is the same function. Of course, you do get a negative, and from the chain rule, you get the frequency pulled out each time. Yeah, some of you might remember this from our pendulum discussion way back in chapter 15 when we started physics. Oops, squared. Physics 123. And again, let me only write 3 frequencies here. But I think you're seeing something quite interesting is you get the same type of function back, but you get a number out in front here. Oops, I should have included that. And it's got a negative and then the frequency squared. Now, here's why I would discuss this. I would say that, okay, what this is saying is if you have an object with a temperature profile, the temperature at different points will change at different rates at different times. And it would depend upon the second derivative. And then notice something interesting about the second derivative. The negative here is not the interesting one. That just means if it's at a high temperature, it'll go down, and if it's at a low temperature, it'll go up. Okay, but the rate is proportional to its frequency squared. So the parts that are really wavy, the parts that have high frequencies, will then change their temperature at higher rates than those at lower temperatures. And so an object that had a temperature profile that had a small frequency compared to a big frequency a little later in time, these, and it makes sense, they have more bend to them, they have more concavity to them. These are going to change at a faster rate than these. So a little bit later in time, of course, this would come down and this would go up, and so maybe the profile would look like this. But these guys would have come down at a much faster rate. And so you would still have some squiggles in here. But you've almost got a uniform temperature and a much quicker rate than these low frequencies. And so depending on your profile, things are going to change pretty quickly. Now, of course, you might also remember from the Fourier series and Fourier transforms that you get sharp peaks in your temperature profile or your graphing profile at the high frequencies. So anything that has sharp points mathematically has to be represented with high frequencies. And according to the physics, then these high frequencies would change their temperature very quickly. And so those ones that got the sharp little peaks, they change very quickly, really quickly, the temperature gradient. Whereas the ones that just have a meandering temperature change, they would take a little bit less. But what I was trying to get you to see then is you could now see the mathematical usefulness then of taking the temperature profile and breaking it down into a Fourier series. And so now you can see mathematically why the heat equation is a great equation to study math 220 in, because it is a multivariable partial differential equation that has some neat mathematical sense, but it's also a good way to show how you may able to solve something that's complex and break it down into a Fourier series. And so it gives us a lot of fun mathematical techniques that are really, regardless of how the usefulness of the physics of them, they're just good mathematical techniques. And so they're kind of cool. All right, and I should have said that with the first video. Well, bye now.